CECO-Environmental is energized by our mission to protect people, the environment, and industrial equipment. Our ongoing commitment to this mission is no small feat, and we take that challenge seriously. It's at the core of how we think, feel, and act. For more than 150 years, CECO has served customers in more than 40 countries through our network of trusted and well-known brands. Our expertly engineered technologies help companies across diverse industries grow their business with safe, clean, and efficient solutions that help protect our shared environment. CECO can improve air and water quality, optimize the energy value chain, and provide custom-engineered systems for a wide range of applications by leveraging our highly refined technologies and years of expertise. CECO is proud to serve our customers in a broad landscape of industrial air, industrial water, and energy transition markets worldwide across our key business segments. Engineered systems, power generation, refinery, water and wastewater, and midstream oil and gas markets require efficient and effective emissions management, product recovery, and water and gas separation solutions. CECO meets these needs with our highly engineered environmental and equipment protection systems. Industrial process solutions. From semiconductor to pharmaceutical production, food and beverage to electric vehicle manufacturing, CECO helps protect the air we breathe, maintain clean and safe workplaces, lower energy consumption, and minimize waste for customers to ensure they meet regulatory compliance standards for toxic emissions, fumes, volatile organic compounds, and odors. CECO provides industry-leading products and services to ensure our customers meet or exceed environmental regulations or other goals. Change the way you do business. Contact us to learn how we help you solve your most critical challenges. Trusted brands, trusted experience, trusted partnerships. We are CECO-Environmental. Accomplish more together, sustainably.
Welcome, and thank you for joining us today for the CECO Certified Continuing Education Series. Today we'll be learning about SCR Emission System Basics presented by CECO-Environmental. My name is Mary Rusnak, and I'm the Global Marketing Director for CECO. And with me today is Jeff Broderick, Director of Retrofit Sales for our Peerless Group. While we wait for everyone to join, I'd like to just do some basic housekeeping and talk about how this platform works, as well as the PDH certification portion. So obviously, if you have sound issues, I'm hoping you could still read the slide here. Things to do if you have any issues during the presentation is check your media players down that little arrow button that can help you and make sure that, if it's muted, unmute. Take a look at the help widget that can walk you through a few items that might help you with the technical issues. And then finally, if you really can't resolve it, try logging back in, out and in, and just using that email that you first got when you registered. A little bit about the platform here. At the bottom of your screen, you're going to see a lot of multiple engagement tools or widgets. Those widgets are all items that you can use to access a lot of different resources. They're all resizable. You can move them around. You can open and close them. So feel free to move everything around to accommodate whatever size desktop that you have. For the slide portion, if you want to maximize the view to full screen, just use the arrows on the right-hand side, and that will make it larger for you. If you have any questions during the webcast, you can submit them through the Q&A widget, which is over on the right-hand side. We want to keep ourselves on track during this presentation, so we're going to hold all of the questions until the end, but you can submit at any time, and if we do not get to that question live, don't worry, we will get in touch with you afterward. So, make sure that you continue to just submit your questions as you go along. A copy of today's slide deck and additional materials are also available over on the resource list. We encourage you to download any resources or take a look at a lot of the links that are available. A lot of information is very useful. You will notice that we have links to Facebook, YouTube, all of our social media. There's also a summary guide in there for anyone who is doing the testing portion today. Hint, hint, that summary could certainly help you with your quiz questions. We also have the information about where you can find more information about CECO certified in the 36 states that we offer PE credits for. All you really need to do, again, hover over the widgets. It'll tell you exactly what they do, and feel free to use all of them. Again, for anyone who is doing the PE portion and needs the credit, the last two widgets, the most important ones for you. The one is the test widget, and that's where you're going to obviously take the quiz questions. And then the final one is the tracker widget, and that will let you know if you have completed all the requirements to get the actual certificate. Once you've completed all the requirements, you'll be able to print it out directly from that tracker widget. Also, just to discuss a little bit, obviously all webinars are very bandwidth intense. Make sure you close all browsers that you're not using, any other things like that, so that you can use up the bandwidth for this. If you have any issue where your slides are falling behind, just hit F5 on your keyboard and that will refresh the page. I've also found that Chrome seems to be the best browser for this platform. Again, any issues that you have, please use the help widget. That will be able to help you with any technical problems. And an on-demand version of the webcast will be available after the event, and you can basically access it using the same link that you used to join us here today. And all the interactivity will remain, and you'll be able to take your test and print out your resources or your certificate at any point in time. So if you have to leave for any reason or you get cut out, you can come back in and continue the presentation and get all the information that you need. Let's talk a little bit about the professional development hours. Today's webinar is worth one professional development hour or credit hour. You do need to be present for at least 50 minutes during this event. You have to complete the test and pass it 8 out of 10. Once you're done with that, you can see there'll be, if you go to the certification widget or the tracker widget, you'll be able to print out your certificate there. I encourage you to keep a record log of all events that you go to. CECO will also keep records for 6 years. That way we'll have information for you if you ever do need it. If you have any issues or any additional questions, you can contact me at that email below. And then just finally, the webinar is 1 hour long, but we are going to keep the actual platform open for an additional half hour to allow everybody to finish taking their tests and printing out all materials that they need. But we will be trying to wrap this up at about 1:30. All right, today's outline, we're going to talk about, obviously, Selective Catalytic Reduction, SCR Systems. We're going to go through the basic parts, look at reagents, what are the methods used to deliver them, what steps should you take with the design, and then best maintenance practices. We're going to start with a poll question, and we have a few of them in this presentation, and you'll be able to actually input your answers on the next slide. So starting off, how much experience do you have with SCR emission systems? Options are, I'm an expert, I have some experience, I have a little experience, I really don't know what an SCR system is. So here you go. Please enter your answers here, and we will take a look at the results in a second. Give it another second here. Okay, let's see what we've got. Okay, so we have here a good portion have a little bit of experience. Some are a little bit more, but it doesn't look like we have a lot of experts, so I think that's great. We've got, I think the presentation that we have pulled together for you today that Jeff is going to work on is going to give you a lot of info and give you that great baseline. So definitely looking forward to having all of you here, and I'm going to turn this over to Jeff, who's really going to talk about SCR emission systems. Thanks, Jeff.
Thank you, Mary, and welcome everybody. Yeah, good to see we don't have too many experts. This is a basic overview of what selective catalytic reduction systems are and how they can be applied. So a little bit of graphic there showing a simplicity of an SCR system. So really it's an air pollution control system. So it's a system that works to control harmful pollutants by providing exhaust stream solutions for industrial air emitters of harmful emissions, and it abates or reduces NOx emissions mainly, but it also can reduce CO emissions. SCR systems can be applied to a variety of custom combustion sources and of different sizes, so SCR is definitely scalable as well. The temperature of the exhaust going through the system is critical for how efficiently it can work, and the performance of SCR systems is being pushed to achieve lower and lower emissions by different federal and local regulations and air permits. So why do we need SCR technology? So as mentioned, it's to help reduce air pollution. So I think most of us has probably heard of the terms ozone and smog. So ozone, some people think of the ozone layer, something we want to protect. So a lot of consumer products have CFCs in them, and those have been reduced over the years to help protect the ozone layer because we need that ozone layer up high. Ozone lower, closer to the ground, can be problematic. So different types of emitters, such as power plants or cars and trucks or factories, emit NOx pollution, and NOx combined with VOCs and heat and sunlight creates ozone down low. And what we see as ozone forms down lower towards us is the production of smog. So something you can see by looking outside. If we're reducing NOx well, you'll see less smog in the nearby areas. So really the main driver for why we want to apply SCR technologies on combustion sources. So what is NOx? What is the thing that we're saying is helping to create smog, which we don't want? They're nitrogen oxide gases. So it's a gas, it's a pollutant that is primarily formed through the combustion process, meaning at high temperature. So in some cases, there's actual nitrogen in the fuel. For instance, coal and biomass and some oils will actually have nitrogen in the fuel that will oxidize into NOx. But primarily, in a combustion source, the majority of NOx is created from what is called thermal NOx. And thermal NOx comes from when the nitrogen reacts with the oxygen at very high temperatures. So as you can see, 1350 degrees Fahrenheit or almost 2500, or Celsius, almost 2500 degrees Fahrenheit, you'll create quite a bit of NOx from the combustion process. And NOx is the combination of nitrogen oxide, NO, and nitrogen dioxide. The combination of those two is what we refer to as NOx. So, as said, it's a driver to reduce air pollution, and in the 70s and 90s, the Clean Air Act by the EPA were set out to help in the reduction of this air pollution. So, the National Ambient Air Quality Standards, NAAQS there, called out 6 different criteria that were leading to this harmful air pollutants, particulate matter, ozone, which we just discussed, SOx, which has to do with sulfur, and then NOx, CO, and lead. And they pointed out many different areas of the country that had worse air pollutants than others. So as you can see by that map, on the coast, the East Coast, West Coast, and some other major areas of the country that have what they were referred to as non-attainment areas. They did not meet the standards set by the Clean Air Act. And those areas were what were first focused on for the installation of SCR systems in this country. So the majority of installations early on were in those regions. Both state and federal regulations help drive the standards that we're trying to meet today. And so in some cases, the state regulations can be more strict than the overall federal regulations. So to help further define SCR, it's Selective Catalytic Reduction. So it uses a catalyst to help reduce the emissions. It's an active emissions control system, which means we are actively injecting and controlling the constituents of exhaust to help reduce the NOx emissions. And we do that with a liquid reagent, which is typically ammonia, through a specialized catalyst. So the ammonia will mix with the NOx of the exhaust gas. Remember, this is all coming from a combustion source, so there's hot exhaust gas being released, and it mixes through a catalyst and results in safer just nitrogen and water vapor. So you can see some of the process there and some of the definitions of what's coming into the catalyst and what's coming out of the catalyst and how the system is helping to reduce the harmful emissions. What are some applications for SCR? So it's a pretty versatile technology for a lot of different combustion sources, and it can be applied to a wide range of fuels. As we know, different combustion sources can run on different fuels. So a boiler or a gas turbine or whatever it might be might have a different fuel. So natural gas is a very common fuel, RFG or gasoline, obviously, different fuel oils, coal, biomass, hydrogen, and even some other what are referred to as opportunity fuels or waste fuels could be combusted and create different varying levels of NOx, many of which can be solved by installing an SCR system. So it's a versatile technology in terms of what it can treat from different sources. It's also versatile on the size and type of combustion source. So combustion is a very broad term and it can be done in a variety of ways. For instance, you could have a burner installed on a boiler, a package boiler, a larger boiler, that obviously combusts a fuel and creates exhaust emissions that has NOx. So a lot of different types of equipment produce NOx because of their combustion process: gas turbines, boilers, engines of a variety of sizes, and others such as heaters and reformers and kilns and incinerators. So it's, again, a variety of fuels and a variety of combustion sources can all be fed to specialized SCR systems to help reduce the air pollution coming from those sources. So we've been calling it an SCR system, and it truly is a system and isn't a single piece of equipment that is controlling the emissions from the combustion source. It's a combination of equipment or subsystems working together in conjunction to achieve the overall goal. Generally speaking, there's some sort of storage for the liquid reagent we mentioned, typically ammonia, that needs to be stored on site to be used in the process. That then needs to be forwarded to the process and controlled in a specific way to make sure you're not using too much or too little of that reagent. And then it needs to be carefully injected, depending on the size of the exhaust and the quantity of exhaust and ammonia being used. There's different methods for how you would inject it and introduce it into the exhaust stream. And again, it needs to combine with that dirty exhaust upstream of the catalyst, mix out in the catalyst, and reduce the emissions in that method. So there's several subsystems that go into making a complete SCR system function properly and efficiently. So as mentioned, there's storage. So typically there's an ammonia storage tank involved with the system, and that's kind of the first step in the process. We need to make sure we have the reagent on site, on hand, to be able to effectively reduce the emissions. So typically, these tanks are designed and fabricated to certain codes of the American Society of Mechanical Engineers. There are standards that need to be met, and a lot of those standards are designed around the safety of storing this liquid. Typically, the size of a tank, and of course it depends on the size of the system and how much NOx needs to be reduced, but 500 to 10,000 gallons of capacity is within the typical range, and you can certainly use smaller tanks or much larger tanks if needed, depending on how much storage capacity is required. Typically, they're large steel tanks. They could be steel, they could be stainless steel. In very specific applications, you could use alternate, plastics or whatever it might be. Ammonia is typically stored under pressure, so the tank needs to have specific pressure ratings, and you need to monitor the condition of that tank. So there's instrumentation involved with the storage. We want to monitor, obviously, the level of the tank to make sure there's enough liquid in there for the process. The temperature, the pressure are important. The ammonia can operate throughout a wide range of temperature, but you need to monitor it to make sure it's not outside of that range. Clearly, pressure is important because it is being stored in a tank. You don't want to overpressure the tank. And then there's some ancillary equipment involved to just make sure the system works and you're able to pump in and out of the tank and efficiently use the reagent in the process. So the storage of ammonia is an engineered system that needs to be carefully designed. So from that storage tank, we go to typically a pump skid, and that pump skid is used to send this liquid reagent out to the process. It also circulates that reagent to the tank to maintain certain pressures and turn over the tank if needed. Typically, we like to avoid single points of failure. So oftentimes on a system, there will be redundancy, and that 2x100 represents each pump able to handle the entire flow of the system if needed. If there was a problem with one of those pumps, the other one could be used in its place. Oftentimes, these are made of stainless steel because of the location of the installation, the harsh environment it might be located in, and the longevity of the equipment. And again, a lot of instrumentation involved with the pump skid, as with all the other parts of the system. We want to monitor certain parameters to make sure the system is operating as we want it. So the pressure, we don't want to overpressurize anything. So there's safety switches, safety valves. We want to monitor the flow and the pressure of the liquid out to the process. We want to make sure that liquid is clean to the process. We don't want to have any tramp material coming from the tank, or that might be some impurities in the reagent. So we filter the ammonia as well in this stage to make sure we're not plugging anything up downstream. And we'll typically monitor the pressure across that filter to make sure we know when that needs to be cleaned. There's obviously going to be some junction boxes and controls involved with the system. So as you can see from the picture, a junction box, and oftentimes this is located next to the storage tank. Ideally, there are certainly specialty situations where this might be remote, but ideally this tank and pump system are relatively close to each other. So we also need to control the amount or the flow of ammonia being introduced to the process. Obviously, the size of the system, how much emissions are being reduced, how much exhaust flow there is, it's going to change the amount of ammonia required going through the system. Every SCR system has its own set flow requirement. So we need to carefully control that flow and how we introduce it into the process. Oftentimes that's done with flow control valves for the reagent, and we feed that into what is often referred to as an AFCU, or ammonia flow control unit. And that ammonia flow control unit is used to take that liquid reagent and vaporize it into an ammonia gas with the use of hot air or hot gases. A very typical way of doing that is to use some fans. Again, just like the pumps, we would often use redundant fans. An electric heater can be used to create the heat needed to vaporize that liquid into an ammonia gas, and we can then control the flow of that ammonia gas to the process through the AFCU skid. So as we mentioned, an SCR system can be applied to a lot of different types of units with different types of fuels and different types of exhaust gases. Because of that, there's not a one-size-fit-all or one design-fit-all solutions for an ammonia flow control unit. So there's different designs that could be used in the process to control the flow of ammonia into the system. So some of these systems use what's called hot gas recirculation, where you're actually pulling exhaust gas out of the combustion source and using that as the heat to vaporize your ammonia. Oftentimes it's on a smaller unit maybe. We use an electric system, which again, ambient fans, taking in fresh air, pushing it through a heater and using that as the heat source to vaporize. Or you could actually combine those two types of systems. So you could actually pull in hot gas and heat that hot gas with an electric heater if you wanted to have to start up sooner. So some regulations are pushing different combustion sources to reduce NOx as quickly as possible. So a combined unit might be used on a larger unit or a unit that needs to start up more quickly and not wait for the process to become hot, but promote that heat more quickly so the SCR system can start up more quickly. So another part of the SCR system is the injection. So how is that ammonia then injected into the exhaust stream? So at this point, we've been on kind of the cold side. Most of the equipment is outside next to the combustion source, but we need to introduce that ammonia into the exhaust flow before it goes to the catalyst. So we need to mix that ammonia out with the exhaust. So we need to, what we call, inject that ammonia. So there's multiple ways to do this. Two very common ways here are with an ammonia injection grid or with actually a liquid nozzle. And they are obviously designed to introduce the ammonia into the exhaust gas. And AIGs are used to do that in the vapor form, whereas an air-assisted injection nozzle would be used to inject it as a liquid upstream the catalyst and use the heat of the exhaust. We'll go into more detail on both of those in subsequent slides. The size, the quantity, and the injection rate are all factors on how you design and size the type of injection equipment used in the specific application. The duct size makes a big difference. How hot is the temperature of the exhaust, and what are the requirements of the system? How much of the NOx in the combustion process does it need to reduce? So as mentioned, there's really two main types of injection systems. Again, the AIG, the ammonia injection grid, is used when you're vaporizing liquid ammonia into ammonia gas and then introducing it into the exhaust. And the air-assisted nozzle is when you're injecting the ammonia in as a liquid directly into the combustion source or the exhaust gas and having it vaporize with that heat. And you can see the different types of equipment there. Again, that would be a representation of an AFCU skid up at the top left, the ammonia injection grid, or AIG, in the middle, an air-assisted injection nozzle, and a direct injection metering skid, which is more of a liquid control skid and not a vaporizer type skid. Obviously, a critical part of the system as a whole is the catalyst itself. All of the exhaust gas needs to pass through this with the NOx and ammonia for the system to be effective and actually reduce the air pollution. So similar, so some of you might be familiar with the catalytic converter that's on your car or your truck. If you've ever seen that, it's a porous substrate that can the exhaust gas, all the exhaust gas passes through it, and it reduces, in that case, CO emissions. This catalyst at a high level is relatively similar to that. So all of the exhaust gas must go through the catalyst to reduce the emissions. So it's typically precious metals that are impregnated onto a porous substrate. So if you were to be looking through a catalyst, you could actually see through it a little bit, but there would be very small holes that you would see. These precious metals are formulated and adhered to the catalyst based on the specifics of the system. So the exhaust flow, the exhaust temperature, the emissions requirements, and how much NOx needs to be reduced are all factors that the catalyst suppliers use to formulate and engineer their catalyst to perform on that specific application. So as you can see there, a picture of the catalyst of a relatively large system. It's typically installed in the field when the system is being built. The amount of catalyst depends on just how much exhaust is going through it. So the more exhaust going through the catalyst, the more catalyst volume we need. And the higher the NOx reduction requirements of the system, the more catalyst volume we need. So there's quite a bit that goes into the sizing of how much catalyst you need to treat all of the exhaust. Catalysts are typically made in modules at a factory, and they're shipped to the site, and then in something like that picture that you're seeing there are installed by qualified professionals, oftentimes requires scaffolding and hoists and things of that nature to make sure the catalyst is installed properly. And in the maintenance portion of these slides, we'll see why that is so important. A little bit more detail on the catalyst. Again, it's installed in the hot ductwork. It takes up the whole of the duct. So you can see in that top left that that's pretty much a square duct there, and it's touching all four walls. There is no bypass around the catalyst. So we can treat all of the emissions. There's a lot of unique designs in today's industry that the catalyst suppliers are able to make, things to reduce pressure drop or operate at higher temperatures or lower temperatures than they've been able to in the past, or treat different types of exhaust constituents. So a lot of specialty products out there. And it's very flexible. It's custom designed for the application. Sometimes the catalyst might need to be a little bit longer. Sometimes the hole sizes or pitch or pore size will need to be different depending on if there's particulate in the exhaust. So you can see there's different hole sizes in that picture on the right, depending on what type of exhaust gas is flowing through it, because not every fuel burns the same, or not every unit burns that fuel the same way. And there's also specialty catalysts that can reduce more than just NOx. It could reduce CO or even VOCs in one layer of NOx. And there are other standalone catalysts that can do different exhaust constituents as well that are not necessarily related to SCR, but might be used in conjunction with them. We have mentioned that this system needs to operate at specific temperatures, so that chart on the right there shows kind of the sweet spot of where the operating conditions need to be, operating temperatures need to be for the reaction to take place. So in addition to the kind of the prime sets of subsystems that go into the SCR system, the storage and the forwarding and handling and the AFCU skids and the injection, there's going to be other systems or ancillary pieces of equipment that need to go along with this to make sure it's fitting up to the combustion source that it's being applied to. So there's going to be some extra duct work involved with having an SCR system. You may need fans to control the flow of gas, to overcome pressure, to cool the exhaust to a certain temperature that might be needed. There's going to be some sort of support structure needed to hold up the system. These can be very large systems in some cases, in which case you also might need to be able to access the equipment. So additional platforms and ladders and other ancillary equipment might be needed. And then it's possible that the emissions might need to be monitored at all times. So if a state regulation is forcing an SCR system to be used on a certain combustion source, they may also require that the emissions, the NOx emissions, be reported on a continuous basis. And there are analyzers that can be installed to accomplish that, to make sure the SCR system is working properly.
And we've hit our next poll question here, and just like the last one, just input your answers in the next slide. So is your company looking at greener technologies or other carbon footprint reduction initiatives? So your options are yes, implementing some now. Yes, we're doing some future planning, a little bit greater than a year. Yes, future planning greater than 2 years or more. And then D, none planned at the moment. So you just implement or input your answer here, and we'll take a look at the results. And hopefully nobody is confused like the bunny was in the previous slide. We'll give everybody another 15, 20 seconds to input their answers and take a look at the results. All right, let's see what we have here. So it looks like we have a good portion have started implementing some different initiatives now, and then obviously quite a few that are in planning stages with something anywhere between 1 and 2+ years. So yeah, it's definitely something that we're seeing across the board in a lot of industries, as well as for us as a company. So good to know. Send this back to Jeff now.
Thanks, Mary. So overall, the system needs to be controlled. It doesn't just operate without any inputs and outputs. There needs to be some amount of control to the system to make sure it's operating with the system it's applied to. So there's an important system that is combusting a fuel for a specific reason, and it needs to the SCR system needs to work in conjunction with that system. So needing to establish a target ammonia flow rate by taking in some information from that combustion unit is important. We can calculate how much is required based on that information, and we can control the system to do that. In some cases, we can use what's called a closed loop system, where we can actually either trim or fine tune, let's say, the flow of ammonia based on using flow meters and bringing that back into the controls to make sure we are flowing what we want to be. Or we could even actually measure the NOx. So previous slide we had mentioned there could be an emissions analyzer on the system, so we could actually take information in from that analyzer and fine tune the control of ammonia flow and other processes to make sure that the emissions are always within the desired range. Most of the time, these systems can operate in automatic, so they're set up with the end user at the particular plant they're at or site they're at, and they can run in automatic when the combustion unit starts up. So does the SCR, or sometimes they're more of a manual process. But there's a lot of controls that go into making sure these systems work properly. Just examples of sketches or graphics of what those controls might look like and how they apply to a system that operates at different conditions. So if you think of an engine and you push down on the gas pedal, your engine's then working harder and there's actually more exhaust coming out of it. So same with a much larger combustion source. All these different sources can operate at different, what we call load ranges or operating conditions. So the different operating conditions would require different flow rates of ammonia, and that all needs to be monitored and controlled. Again, because there's multiple subsystems involved with a full SCR system, monitoring, the tank level or the pressure of the ammonia or the heat of the exhaust, all of these things are important to make sure the system is operating the way it's designed to and reducing the harmful pollutants. So what types of reagents can be used with an SCR system? So ultimately what we need is ammonia gas being mixed out in front of the catalyst. The catalyst is using the ammonia as a gas, but there's multiple ways to achieve introducing the reagent into the system to produce that ammonia gas. Namely, there's three main ways to do that. Anhydrous ammonia, which is already in gaseous form, can be stored at the site and controlled and sent over into the process. This is a method that's been used for many years, but it does have some safety concerns. So anhydrous ammonia or ammonia gas is very dangerous to the personnel working at the site. So there's a lot of factors that need to be considered in how it's stored and how it's transferred and even how it's delivered to the site. So that can be a little bit arduous for some locations and a little bit too dangerous in certain applications. So there's been, over the years, ways to figure out how to make it a safer process. One of those processes is to use aqueous ammonia, which is in a liquid state. So it's essentially diluted ammonia, and you can store it under relatively low pressure in a similar type of tank. And the most common way the ammonia is diluted is down to 19%. 29% is also used, but the more common way is a 19% ammonia solution. Still has some safety concerns, but it's not quite as dangerous because it is a diluted reagent at that point. The safest version is to use urea. So urea is also known as DEF, or diesel emissions fluid. That's widely used in automotive applications and has been applied to larger systems as well. And there's different concentrations of urea as well. The main selling point of urea, or the main driver of using urea, is because it can be stored without any safety concerns. It is non-hazardous and is not dangerous to personnel, but it does need to be converted at high temperature to ammonia. So there are some challenges associated with that. So again, anhydrous ammonia, if it's already in gas form, it's a very straightforward way of controlling the SCR process. Essentially, what you do is you use the AFCU, the piece of equipment we've already discussed, and you use blowers to feed that into the process. So because it's already in gaseous form, there's usually no need to then vaporize it. So it's a very straightforward way of feeding the ammonia to the SCR system. Low power consumption, in some cases just overall less equipment, and very straightforward. If the decision was to use an aqueous ammonia reagent to be a little bit safer, in order to introduce it into the catalyst, we need to then vaporize the water out of that reagent. So a little bit of an extra step there to use aqueous ammonia instead of anhydrous, because we need to vaporize the water out of the reagent and then introduce it into the system. So could be a little bit more cost on the AFCU side, and it could be employed with either AIG or direct injection. And then a little bit safer, but a little bit more complicated in some ways, is urea. So again, this would be stored as a liquid. So the water still needs to be vaporized out of it, but it also needs to be what we refer to as decomposed into ammonia. So it needs to be heated to a higher temperature, more than just vaporizing the water out of it. You actually need to convert the urea at high temperature into ammonia for it to be used in the process. So at this point, you have a higher cost AFCU, larger pieces of equipment in order to vaporize and decompose the urea into ammonia. So those are the three main reagents there. As an example, to kind of point out some of the complexities of each one, in a anhydrous system, if you had a unit that had about 250,000 pounds an hour of exhaust flow, and you were trying to reduce the NOx emissions from 50 ppm down to 5 ppm, or a 90% reduction. If you had an anhydrous ammonia system, you can see you need about 6.3 pounds an hour of ammonia to accomplish that. That's going to be a relatively small AFCU skid with a a small blower on it and probably don't need any electric heat there because it's already in gaseous form. That same system, if it was an aqueous ammonia system, same amount of raw ammonia needed, but because it's in liquid form, there's actually more pounds of it. So you have 33 pounds of it, or 4.3 gallons per hour is being injected into the system. So the AFCU now needs a heater on it. So you need 50 kilowatts of electric heat that you wouldn't have otherwise needed with an anhydrous system, but you're using a safer alternative. And again, one step further towards the safety, if we were using a 32% urea system, same amount of ammonia needed to go through the catalyst again, but that AFCU skid needs to be larger to not only vaporize the water, but decompose the urea into ammonia. So now you're stepping up the AFCU size to a 10 horsepower blower with 200 kilowatts of electric heat to vaporize and decompose that urea into ammonia to be fed into the system. So just an example of how each one looks on a similar combustion unit and what the trade-off for complexity versus safety might look like. We spoke a little bit about ammonia storage and handling in the previous slides, and there are some differences in how urea is handled. So just going through that, oftentimes urea can be stored in a plastic or stainless tank because it is corrosive to carbon steel. So the storage tank for urea is going to be different than what you would see for ammonia. Using stainless steel throughout is required because of the corrosion. One of the challenges with urea is it will freeze or crystallize at low temperatures, but those temperatures are much higher than what it would be for ammonia. So we need to keep an eye on the temperature of the tank and the temperature of the piping to make sure there is no freezing of the urea in the process, which would plug up the piping and cause major problems with the system. Again, just like ammonia, how much storage is required on the system and how big will the tank need to be. Oftentimes these tanks can be made as double wall tanks, so you don't necessarily need a different containment area around them. And also because it's a non-hazardous, you may be able to get away with a little bit less safety factors or safety equipment than you would with an ammonia system. They're also available in what they refer to as totes. So these totes that you see on the right could actually be shipped to the site and used in the process in lieu of a larger tank. We've touched on the two main ways you can inject the ammonia into the exhaust stream, namely the AIG and AFCU that we've been discussing, and what we refer to as direct injection, where you're actually injecting the liquid directly into the exhaust stream. So those are really the two main methods. The vaporizer in AIG is known as a little bit more of traditional solution, and the direct injection is a little bit more of a so-called advanced solution. So again, we're on the AFCU side and AIG side, we're taking the reagent from a tank, pumping it, putting it through an AFCU to control the flow, and the ammonia injection grid is an array of piping with multiple holes in it to control and distribute the flow of ammonia through the system. It's a very efficient way of distributing the ammonia in front of the catalyst, and you can mix it all out in a very short distance, which is the advantage of it. This type of system is typically used on larger units with large catalyst cross sections because it's able to distribute that ammonia so efficiently all the way across the gas path. This type of system does require that the ammonia be vaporized upstream of the process. So ammonia gas must be going through the AIG, not liquid ammonia. And there's a graphic that shows some of the analysis that goes into the distribution of ammonia. You can actually use computer models to take a look at how effectively the AIG is working. The ammonia to NOx distribution is a key factor to how the SCR will perform. If there's too much ammonia in one section of the exhaust compared to another, the system will not function well, and it will not reduce NOx efficiently. can see some of the advantages of a well-designed system there in terms of extending catalyst life and shortening the overall footprint. Again, more information on the AIG, the design of it, the piping, the exit hole size, the locations of those holes are all important and need to be detailed out in order to properly design the system. One thing that needs to be taken care of is to make sure that the AIG does not plug up. A direct injection system can be applied to some systems, but not all. So some of the feasibility considerations that go into that, is there a duct burner? What is the size of the duct that needs to be injected in? What's the residence time and how much mixing is needed? All of those things need to be considered when analyzing if direct injection can be used or if a traditional system should be used instead. If it can be used, there are some operational benefits to injecting it directly as a liquid. It requires less equipment because the blowers and heaters are not required to vaporize the ammonia upstream. So less equipment means less cost and less operational cost. It also would result in less maintenance because there's less equipment, there's less things to maintain, and fewer moving parts means just a bit of an easier operation for the system as a whole. So similar equipment that we've talked about. Obviously, you still need storage. You still need to control the flow and still need to inject, but the details of those systems are just slightly different based on not needing to actually vaporize the ammonia first. Still all needs to travel through a catalyst and needs to be evenly distributed across the face of that catalyst. But the details of those systems look slightly different. Pictures of the same equipment to show some scale of what it might look like on a package boiler, a 1,000-gallon tank next to a control system that has pumps in a control panel and a reactor box that houses the catalyst.
Okay, we're getting to the end of the presentation here. Give Jeff a quick break. So we're going to cruise through this one pretty quickly, though. Where can SCR emissions equipment be used effectively? You have several choices there. Give you a little bit of time here, 15, 20 seconds to make your selections, and we're going to take a look at the results. Okay, let's see what we have here. All of the above. All right, you guys are paying attention. That's awesome. Good job. All right, Jeff, we're in the end here.
All right, what steps do we need to take when we're looking to design an SCR system? So some of the overall considerations, just how low does the NOx need to go for the SCR? Have other NOx reduction methods been applied? So could the NOx be reduced at the combustion source instead of with this after treatment type of system? Again, we've talked about the types of fuels and units that it could be applied to and how versatile it is, but there may be some restrictions based on the specifics of either that fuel or that specific combustion unit. Oftentimes the space is a major concern for installing an SCR. These are not, these do take up space, as we've seen from some of the photos and graphics. So does the site have the space to control this? And then does the plant have the utilities needed? And can the existing equipment work with an SCR system, or will some of that need to be replaced? And then obviously, will the system meet the permit compliance that was written to regulate the combustion source so that the system can meet the needs of the air permit and the facility that it's working in. We've already reviewed that it's a flexible type of system with the units and fuels that it works on. It's a highly effective system in terms of how much NOx it can reduce, 95% or more in some cases. Again, the system, the catalyst specifically, needs to be located in an area of the exhaust that is at the proper temperature, 350 to 800 degrees typically. And what are the inlet and outlet conditions of the system, and how do we design around that? There are some poisons in specific exhausts that can limit the use of catalyst in a system and therefore limit using SCR as a whole. Some of those are listed there. If there's too much particulate, or dust or ash, that could coat the catalyst and cause problems, just like it would plug up a filter. It could plug up the catalyst, causing performance issues. Ammonium and sulfur combinations can be problematic because they can actually form some solids and mask the catalyst. Specific metals can either mask or actually poison the catalyst and make it ineffective. And there's some other additional poisons listed there. And another thing we want to avoid is actually spraying water or an actual liquid onto the catalyst, which is why we need to design the system carefully to make sure we're not spraying any liquid urea or ammonia onto the catalyst when we're doing direct injection. A couple examples of the size of what some of these systems look like, and how the footprint or the layout of the system depends on the space availability. You need to be able to fit the catalyst, the reactor housing, and the ancillary equipment, the tanks and skids and other stuff, to fit into the location which the SCR system is being applied. Also need to take careful consideration about how much power is being used, and if there's air or other utilities needed to operate the system. CFD is a major tool used to design these systems to make sure the ammonia is mixing well with the catalyst. So computational fluid dynamics is a engineering tool we use to verify the system will meet the performance in terms of mixing and pressure drop and different functions. And here are some examples of the outputs of some of the CFD models in terms of predicting flue gas flow, the exhaust gas profile, the ammonia spray simulation, and how that all interacts with the catalyst to evenly distribute the NOx and ammonia to meet the performance requirements. An example photo here of how these systems may be able to be retrofit on the specific units. So these were two biomass boilers of a similar size, and you can see in the top right and bottom right the before and after pictures of just how large some of these systems can be as compared to the equipment it sits next to. So obviously pre-design planning needs to be done to make sure that you're going to be able to fit the system with the rest of the facility. Some best practices for maintenance to make sure the system lasts the design life. The AFCU, it controls the flow of ammonia, so that needs to be inspected for any type of fouling or plugging. Obviously, the catalyst is an important part of it, and that needs to be maintained and cleaned at certain intervals. We talked about the filtration of ammonia and how that needs to be pure to make sure there is no impurities in the reagent that lead downstream and cause problems. The ammonia injection grid needs to be free and clear of any debris to make sure the ammonia can flow through and be evenly distributed. And then general maintenance, like any other system, on any sort of moving parts or transmitters. If there was to be any exhaust gas bypassing around the catalyst, it would be untreated exhaust and none of the NOx would be reduced. So any sort of problem with the catalyst or shifting of the catalyst or issue with the seals or gaskets between the catalyst need to be addressed and fixed as soon as they're known, so the system can meet the performance required of it. And those are just some examples of how that may look in the field. And then tuning of the system. So the system, all of these types of SCR systems have some sort of tuning method that can be done to make sure the amount of ammonia going into the process is what is required and that it's being evenly distributed and can be measured. So in some cases, there's a tube test grid included downstream of the catalyst that can actually take measurements of the emissions at specific locations to make sure the ammonia injection grid or ammonia nozzles are performing well and evenly distributing the ammonia across the catalyst phase.
Thank you, Jeff. Now, we know we threw a lot at you there, so don't forget that we do have the slide deck over in the resources area. And if you asked a question and we do not get to it live, don't worry, we will get back to you. Just a reminder, you do need to fulfill all the requirements to get the certificate for PE credits, so 50 minutes, and you need to answer the questions, the quiz questions appropriately. And again, a reminder, those last two widgets, where you test and where you track. And let's take a look at a couple questions here. I'm going to push one of these. All right, so what is the difference between SCRs and SNCR, and why would you choose one over the other?
That's a good question. The main difference between an SCR and an SNCR is the catalyst itself. So selective catalytic reduction versus selective non-catalytic reduction. So there is no catalyst involved with SNCR. Why choose one system over the other? An SCR system can reduce more NOx than an SNCR system because of the presence of the catalyst. So it's a bit more efficient of a NOx reduction system. And not all combustion units can utilize SNCR.
Okay. And let's see if we can get through at least a couple more here. What kind of precious metal is used in the catalyst? Gold, silver, platinum, something to that effect?
In some of the catalysts, there's different combinations of precious metals. Tungsten, vanadium, zeolite are others, platinum and palladium in some cases as well. It really depends on the application and temperatures and other factors.
Okay. And we want to be respectful of everybody's time, so we'll do just one more. And again, don't worry, if we didn't get to your question, we will definitely reach out to you with an answer, okay? Last question here. So what sort of maintenance is required on the catalyst, and what is the typical life of catalyst?
The amount of maintenance is going to be dependent on the type of fuel and exhaust constituents going through it, but it should be inspected, annually, at least if possible. A light cleaning of the catalyst should be done when possible to get any debris off the face of it. And typical lives, again, it depends on the application, but I would say if we needed to say what was typical, 5 years.
Okay. All right. Thank you, Jeff, so much for the presentation here. And I hope that everyone here, thank you for attending, that you enjoyed it, and that it was something that you found useful. CECO Certified does have a good library of on-demand events. If you go to CECOcertified.com, I believe we're up to 12 or 13 events that are available for you to take at any point in time, whenever convenient. And we have at least 4 or 5 more of these planned this year. So hopefully we'll see you at a future event. We are going to go quiet now, but I'm going to leave the platform live for everyone to finish up their quiz questions if needed, print out resources, certificates, whatever the case may be. But again, just thank you so much for attending, and we hope to see you at a future event.